In Chapter 13, we will continue our study of trigonometry by transitioning from working with triangles to working with circles and circular motion. Before we start, I want to make sure that I identify some of our major terms. The first is the term arc length. It's the length of some section of the circumference measured around a circle. And we always label that with the variable s. A radian is an angle that we create. It starts from the center of the circle to the edge, and when our arc S is equal to the radius, so this edge here is going to be exactly equal to the radius that I just drew, we call that 1 radian. We use the angle theta, and we know that theta, the number of radians that we're given, is always equal to the length of the arc divided by the radius. So 1 radian is when the arc is equal to the radius. If the arc is double the radius, so again, let's say I've got a theta, and give that arc length 2, and the radius is 1, then we've got 2 radians. The sector is this wedge here that's created by the central angle of a circle. Here we'll start with the formula for the circumference of a circle. What I'm going to do is begin with my theta, the angle measure within the circle, and I'm going to let theta be one complete revolution. So if I start here, theta is actually going to swing all the way around one full revolution, which means that the arc length is equal to the circumference of the circle, and I can substitute that into my formula. If I want to calculate the value of theta with regard to this, I need to remember that theta is equal to the ratio of arc length divided by the radius. Well, in this case, arc length is 2 pi r. So I can substitute that into this formula. These r's cancel, and what I find out is that theta on a complete revolution of a circle is 2 pi. That means that one revolution is equal to 2 pi radians. Now if you notice, I don't usually write out the word radian. If there's no unit of measure given on an angle, then that angle is in radians. We can now use this information to convert degrees to radians and to convert radians to degrees. To begin with, we say that we agree that 360 degrees is equal to 2 pi radians. Well, what would 1 degree be equal to? In order to do that, we can just divide both sides of this equation by 360. When we do, we end up with 1 degree here, and we end up with 2 pi over 360 on the right-hand side. This can be simplified so that 1 degree is equal to pi over 180 radians. We use this ratio anytime we want to convert from degrees to radians. When going in the other direction, we would again say, okay, well, 2 pi radians is equal to 360 degrees. Well, what would 1 radian be equal to? To do that, I divide by 2 pi on both sides. This cancels, and I'm left with 180 over pi. This is what we use to convert from radians to degrees. One way to remember this: our angles in radians are almost always given in terms of pi, which means that if you want pi in the answer, it must be in the numerator. If pi already exists, then you want pi in the denominator so that they can cancel. Continuing on, we'll talk about arc length and sector area. We'll start with using the ratio that we have for radians. We've already said that radians are equal to the arc length, there's our arc length, divided by our radius. Well, this can certainly be arranged so that we can actually say that the arc length is equal to our angle in radians times the radius. When we talk about sector area, which we call A, we need to start with the area of a circle. And I will denote that as A sub circle, and that is equal to, not a 2, pi r squared. Well, if you notice, the sector of this circle is proportional to the area of the entire circle. So we could actually say that the area of this sector is proportional to the area of the circle. Just like the measure of the central angle of this sector is proportional to the measure of the central angle of a circle. We would denote that as theta being the central angle of the sector divided by 2 pi radians as the measure of the central angle of the circle. What happens is that these two proportions actually become equal. So with A being my sector area is proportional to pi r squared, that's the area of my circle, that's equal to the same proportion of theta over 2 pi being one complete revolution in a circle. From here, we actually could solve for A, which would give us a formula for sector area. In order to do that, I simply clear this denominator by multiplying by it on both sides, and I get that A is equal to pi r squared theta over 2 pi. Here, pi cancels out, and I have r squared theta over 2. And to avoid keeping this as a complete fraction, we could simply rewrite this as 1/2 r squared theta and going back, way back to this original formula that I started with, I know that r times theta is equal to s. So I could say, here I've got 2 r's and a theta. I could substitute that with s, and I would get 1/2 r times s. That is the formula for the area of a sector of a circle. The next portion of our discussion deals with what we call linear and angular speed. You are all familiar with linear speed. It's just speed. It's that formula, distance is equal to rate times time. But what we'll talk about now is the linear speed traveling around a circle. So it says a particle is moving with a constant speed, v, that's our rate, around a circle of r centimeters. If it travels s centimeters, s is the distance, in t seconds, then what's the formula? Well, I can replace a few things in this equation and say that s is my distance, v is my rate, t is my time. We can rearrange this so that it is solved for v, our constant speed, in terms of the other variables, and we would get v is equal to s over t. Remember that s is the arc length of the particular circle that we're on. We probably will need r in order to find that arc length. In this particular example, our units here are centimeters per second. Angular speed is a little bit different because it's saying that we're moving through an angle of theta radians. So now we're still traveling in a circle, but instead of measuring the distance around the circle, the speed that we're traveling around this circle, think of it more like the hands of a clock. How quickly are those hands rotating through a particular angle? That's our angular speed. So in this example, we're moving through an angle of theta radians. That's kind of our distance. Our angular speed, that's our rate here, is called omega, even though it looks like a W. And t is still time in seconds. So we can say that our distance is equal to our rate times time. This can be rearranged in a variety of ways to solve for whatever it is we need it to be solved for. So in this case, we'll solve for omega, the angular speed. So omega is equal to theta over time. The units on this are radians per second. Now remember our arc length formula. S is equal to theta r. Well, I can replace S in this equation with that, and I would get that the velocity is theta r over t. We tend to write it r theta over t. And we learned through our formula for angular velocity that theta over t is the angular velocity, so we can actually replace that in the equation as r omega. And what we can discover is that our linear velocity is equal to the radius of the circle times the angular velocity. Now that I've given you a slew of information, let's do a few examples. We are going to convert 135 degrees to radians. So I will set up a proportion. 135 times, now is it pi over 180 or is it 180 over pi? If I think about it, I want pi in my answer because I represent radians in terms of pi, so I will multiply this times pi over 180. I can simplify this, and the way that we write this is 3 pi over 4. So 135 degrees is the same as 3 pi over 4 radians. So the next example goes the other direction. Convert 4 pi over 5 back to degrees. So here I have pi and I need to get rid of it. So I will multiply by 180 over pi. When I do that, these cancel. And in simplifying, I can calculate that this is 144 degrees. Here I've got a circle with radius of 3 centimeters, and I've got a central angle at 80 degrees. I will probably want to sketch that. There's 3 centimeters, there's 80 degrees. I need to find the length of the intercepted arc. That means find this arc length, and then find the sector area. The first mistake that most of you will make is not converting 80 degrees into radians. So let's make that Very big important step number 1. You need to convert to radians. You cannot work this with an angle in degrees. So 80 degrees times pi over 180. And this is equal to 4 pi over 9. I will not accept answers that are in decimal form and rounded. I want your radians to be given in terms of pi unless I specifically state otherwise. So now we have something that we can work with. And I need arc length. Formula for arc length, S is equal to R times theta. So that's 3 times 4 pi over 9. So this is equal to 4 pi over 3. And arc length I can accept as a decimal. In this case, we'll just round it easily to 4.2 centimeters. For sector area, I will need the formula 1/2 r squared theta. Notice that I'm not using the sector, the arc length that I just calculated. I'm using information that was given to avoid any mistakes. So that's 1/2 3 squared times 4 pi over 9. Those will cancel. This will cancel. And my area is equal to 2 pi. Units on that is square centimeters. I will accept area either in terms of pi or as a decimal. Either way is usually okay with me. Now for a word problem. We have a record. I know you guys probably don't know what a record is. It's what people used to play to listen to music. The radius is 15 centimeters. If the angular speed is 10 pi over 9 radians per second, find the speed of a point on the rim. This right here, find the speed of a point on the rim. What it's telling you is linear speed. That's what that means. So I'll start by drawing my record, and knowing that it is 15 centimeters. Omega, the angular speed, is 10 pi over 9. The formula that I need to relate linear speed to angular speed is that linear speed is equal to the radius times the angular speed. Well, luckily I just got all that information. The radius is 15, the angular speed is 10 pi over 9. I can simplify this. 3 goes into 3 times and 5 times. So that becomes 50 pi over 3. And this is a word problem, so I would say the speed of a point on the rim is 50 pi over 3. And here I'm looking at centimeters per second. So we're going to take that record in the previous problem and we're going to play it for 31 minutes. And we want to know how far apart 0.6 centimeters from the center is going to travel. So we'll start by taking a look at our original record with its radius of 15 centimeters. Now we're going to identify a point that's 6 centimeters from the center. We now have a new circle. And it's this circle with the radius of 6 centimeters. We already know the angular velocity that this record is moving through because we've been given that information in the previous problem. it was 10 pi over 9 radians per second. So what we can do is we can use that, first of all, to find the linear speed that this particular point is traveling through. So remember that linear speed is equal to the radius times the angular speed. Well, here our radius is 6, our angular speed is 10 pi over 9. So that will give us a linear speed of 20 pi over 3, and that is centimeters per second. From here, we need to find the arc length. Remember, if we're talking about a point on the edge traveling, we're talking about an arc length. The problem is we've been given a certain amount of time in minutes, so we need to convert that into seconds before we can proceed. So 31 minutes would go in the denominator here, seconds in the numerator here, and we would get that to be 1,860 seconds. Now we can use our formula that relates linear speed and time with arc length s. And that formula is v is equal to s over t. So I've been given linear speed v, 20 pi over 3. S is what I'm trying to find. T is 1,860. If I multiply by 1,860 on both sides, I end up with 12,400 pi is equal to s. So what I can say is a point 6 centimeters from the center travels 12,400 pi centimeters.